Hi, my name is Jun Wang.
My name is Evan Floyd. We are assistant professors in the Department of Occupational and Environmental Health, the College of Public Health at the University of Oklahoma.
This is the Laboratory for Aerosol Science and Health Engineering Research.
Today, we will be piloting our idea for a smart poster. This idea came to me in 2013 when I noticed at a particular conference that the posters were being judged before the authors had an opportunity to give their oral presentation.
So Dr. Floyd today will assisting me to present my research on metal film emission from plasma cutting. And if you have any questions or suggestions, please send us emails through the address here. Thank you. Plasma cutting is a thermal cutting process that's very commonly seen in oil and gas, manufacturing and construction industry. It is very useful when you cut thick and heavy stainless steel. The idea of plasma cutting actually comes from plasma welding in the 80s. The principle is by shooting out air or inert gas from the nozzle and applying high current to the nozzle to form an electronic arc. The arc will then plasmatize the air. The plasma arc will melt the metals along the line, just like this. During the process, a lot of hazardous air pollutants may emit from the metals being cut, such as stainless steel. We have chromium, nickel, and manganese in stainless steel. Chromium can form hexavalent chromium, which is a carcinogen and has a very low kernel exposure limit. Nickel is also a carcinogen, while manganese is a neurological toxin. The particle size of these metal particles are also critical for their health effects. The aerodynamic particle size of them will determine which regions they will deposit in the respiratory tract. Up to date, there are very few studies focused on plasma cutting. The goal of this study is trying to characterize the impact of the operation parameters, specifically arc current, on the physical and chemical properties of the film, such as total film generated and concentration of hexavalent chromium and other inorganic oxides, and particle size distribution and morphology of particles. A conical metal film chamber was constructed according to American Welding Society F1.2 2013 specification. There are two glove holes on each side of the chamber, allows me to operate in plasma cutting. The tinted glass acting as an observation window. The sampling inlet here allows the particle size measurement and particle imaging. The Gell-Mann Hurricane air sampler is able to create up to 2 cubic meters per minute airflow. In this study, it's configured at 0.5 cubic meters per minute. The air and the film will be drawn through a 90 millimeters of glass fiber filter. In this study, we are using an inverter plasma cutter with the arc current ranging from 20 amps to 50 amps. The stainless steel plate we are cutting is 304L stainless steel. It contains chromium, nickel, manganese, carbon, nitrogen, phosphorus, sulfur, and iron. The thickness of this plate is 3/16 inch, and the cutting time ranges from 5 seconds to 30 seconds. Now, I'm going to show you a 10-second sampling period. And this is how the filter looks like after the sampling. The amount of film collected on the filters will be determined gravimetrically. Each filter will be weighing 3 times. Total film generation rate will be calculated by dividing the film mass by arc time. After weighing, each filters will be cut into halves. Each half will be subject to different extraction method. The samples will be extracted into these 5 ml aluminum solution vials. Chromate will be analyzed using NIOSH 7604 method, while the other inorganic oxides such as nitrate, phosphate, sulfate will be analyzed following NIOSH 7900 method. The ion chromatography with the conductive cell has a detection limit roughly about 0.1 ppm. The particle for size measurement will be sampled through this inlet on the chamber. The location of this inlet is approximately bracing head. The aerosol samples will be delivered to the SMPS with a flow rate of 1.5 LPM. The sheath airflow of 3.F0 LPM will provide a size range of 10 to 500 nanometers. Between each measurement, we're using the high volume airflow pump to purge the chamber. The coarse fraction of the aerosols will be measured by this aerodynamical particle sizer with a flow rate of 1 liters per minute. The APS will provide a size range of 0.5 to 20 micron. The morphology of the particles will be imaged through transmission electron microscope. A TEM grid will be holding to the same sampling port used for size measurement. For all the experiment, the samples were taken at least a triplicate. The comparison between different groups was done using one-way ANOVA followed by a home SIDEX pairwise test. The total film generation rates were increased proportionally with the arc currents from 16 mg per minute at 20 amps arc current to about 180 mg per minute at 50 amps arc current. The high currents provide a deeper cut with more energy and temperature input, causing more metals being airborne. The concentration of hexavalent chromium and other inorganic oxides were directly correlated to the oxidation levels. The filter colors and each arc current gives a rough idea of the oxidation level, with the highest current producing a darker brownish color filter. Concentration of hexavalent chromium range between 72 to 150 microgram per cubic meter. Although this is much higher than the OSHA permissible exposure limit of 5 microgram per cubic meter, we cannot directly compare them because the worker only breathes in a fraction of the film in 8-hour work shift. The presence of nitrate and nitrate in the film is interesting. They were the oxidation products of nitrogen in stainless steel and the surrounding air in the arc zone, while nitrate ranged from 200 to 500 microgram per cubic meter and nitrate around the same level of hexavalent chromium. The result shows nitrogen oxides concentration can be related to the hexavalent chromium concentration, which provide a possible way to use NOx as a marker for hexavalent chromium. The trace amount of phosphorus and sulfur in stainless steel also contribute to the phosphate and sulfate in the samples around 20 to 50 microgram per cubic meter, but there was no statistic difference among arc currents. In the fine fraction of the particles, the geometric mean size shifted from 100 nanometer to the large side around 200 nanometers with increasing arc currents. The more energy feed into the system with a higher current promote the intercoagulation and agglomeration of the ultrafine particles, give a large mean size. The coarse fraction shows a similar trend, with more total counts of particles produced at higher arc currents. Exceptions were at the median arc current 35 amps. It gives the lowest total count of particles. The low arc current cutting doesn't penetrate the 3/16-inch stainless steel plates, while the highest arc current gives the wide and deep cut. So at the low arc currents, a hot metal pool was formed in the arc zone, vaporized metals, while at the high arc currents, the high temperature also melted a significant amount of metals through moving the cutting lines. So at the median arc, which gives the cut done but has a lower temperature, so the vaporization of metals are at a minimum, thus produce a low count of particles. The TEM images confirm the existence of the nanoparticles in the cutting film. There were chain-like agglomerates formed from the coagulation of the primary ultrafine particles. There were also large spherical particles formed from the coalescence of the metal particles. The study showed plasma cutting performed on stainless steel will emit a high concentration of aerosols in ultrafine and micron range, loaded with hexavalent chromium in the film. The higher the arc current, the more total film and the particles generated. Hence, we want to make two suggestions. First, when choosing appropriate current, choose the minimum one that can penetrate the plate of thickness, such as 35 amps for the 3/16-inch 304 stainless steel using this study. Second, we suggest the proper respiratory protection and adequate ventilation being available in the workplace to avoid overexposure. The correlation of nitrogen oxides with hexavalent chromium under same oxidation levels gives a possible way to faster determine the hexavalent chromium level in the workplace using a low-cost NOx sensor and using nitrogen oxide as an internal marker. Future works will include the task-based and work-shift per-node sampling study in the metal fabrication shop and determine the other toxic metals in the film, such as nickel and manganese, in which one in vivo study will also be carried to determine the film toxicity. We would like to thank the Oklahoma Medical Research Foundation for providing the TEM instrument access, and we would like to thank Dr. C.Y. Wu for providing the testing plates.
We hope you've enjoyed this smart poster presentation, and I thank Dr. Wong for being willing to let us pilot it with his research. If you enjoyed this, please let us know. If you've got some comments or criticism that you'd like to give us, we'd also like to know that. Thanks.